This project was for California State University Los Angeles' 3D printed glider project, Team 202A. Our members consist of 3 electrical engineers and 2 mechanical engineers. Dilio Matias, who is in general responsible for all electrical components. Aryav Balia, who specifically focused on the control surfaces. Velazco, who was responsible for the morphing wing mechanism. Edgar Quintero, who was responsible for the fuselage and control surfaces. And Anthony Perez, who was in charge of the morphing wing mechanism and wing design. Everyone in this was also partially responsible and involved in the assembly and at one point or another during the project.
Hello, my name is Velazco, and I will be introducing the objective for our project. So, for our project, we are designing and building a 3D printed glider that can be launched using a catapult and controlled remotely through an RC system. The big goal here is to create something that's light enough to stay in the air for a long time, but also strong enough to survive a high speed, high force launch. That means we need to design something that's both aerodynamic and durable. This is not an easy combination. On top of that, the glider needs to be portable, so we're looking at options like folding wings to make storage and transportation much easier. We're using 3D printing to manufacture most of the parts, which lets us quickly test and improve our designs. The glider will include servos to move the wing surfaces during flight, and it'll carry onboard sensors to help keep it stable and collect data we can review later. And that data is really important because it helps us figure out what's working and what needs to change after each test flight. Throughout the project, we'll be looking at a number of key requirements, such as size, weight limits, wingspan, and making sure our glider is compatible with the catapult launch system. We'll also be running simulations, doing wind tunnel tests, and analyzing how the air and forces affect the structure using tools such as CFD and finite element analysis. Our goal is to use all of this information to refine the glider over time, making it more reliable and better performing with each version. By the end of the project, we're aiming to have a fully functional RC glider, complete with detailed test results, design documentation, and some takeaways that can help with future designs. This is very much a hands-on project that brings together aerospace design, 3D printing, and real-world problem solving. And this is giving us the best chance to turn theory into something that actually flies. Now I'll go over some key specifications and limitations of our 3D printed glider design. First, the total weight of the glider is limited to 1 kilogram. This constraint is crucial for ensuring that the glider remains lightweight enough to achieve a long glide duration, especially since it's unpowered and relies solely on aerodynamic efficiency. Next, the wingspan must at least be 1.5 meters. This larger span increases the lift-to-drag ratio, improving the glider performance and helping the aircraft stay airborne for a longer time after a catapult launch. It also provides enough surface area to incorporate control surfaces and our morphing wing mechanism. Speaking of which, one of the most unique features of our glider is the morphing wing mechanism. This allows the wing to dynamically change shape during flight, such as adjusting camber or span to optimize for different flight phases like launch, glide, or descent. It's controlled using onboard electronics and plays a key role in maximizing aerodynamic efficiency. Finally, a major constraint is that the glider is designed with no motor. This means we have no onboard propulsion, and as a result, every decision we make, from the structural design to the control strategy, must focus on minimizing drag, maximizing lift, and ensuring stability throughout the unpowered flight. This limitation pushes us to get creative with our control systems, materials, and aerodynamic choices.
Designing our airfoil, things we took under consideration included lift and drag coefficients, camber and thickness of the profile, and angle of attack. Lift refers to the forces helping an object rise. These forces oppose gravity and act perpendicular to the direction of relative wind. Drag refers to the forces opposing an object's motion and acts parallel to relative wind. To maximize our time of flight, we attempt to maximize lift while minimizing drag. Camber refers to the asymmetry between the top and bottom surfaces of the airfoil. It contributes to lift by altering a profile's pressure distribution and airflow. Thickness of a profile helps increase lift at lower angles of attack at the cost of higher drag. Angle of attack refers to the angle between the profile's chord line and relative wind. Different airfoils will prove more efficient at different angles of attack and different Reynolds numbers, or rather, different speeds. The airfoil we chose as reference for our design is the NACA 4415. The numbers 4415 indicate certain dimensions. The first number refers to the maximum camber as a percentage of the chord length. The second indicates the location of the maximum camber in tenths of the chord. And the last two digits indicate the maximum thickness. The image below shows our profile. Its camber design and thick profile provides a smoother reduction of lift, especially at lower Reynolds numbers. This will give our gliders, pilots, and motors a little bit more time when attempting to stabilize the glider's position after reaching stall, possibly preventing an abrupt end to the flight. This can be seen in the figure to the right.
This third iteration of our wings maintains a very similar design and structure to the first and second prototypes. It maintains the same taper, same profile, and very similar assembly methods with very slight modifications. The majority and bulk of the changes made to the wings come in the addition of the servo motor and the supports around that cavity that would be used to act as the motor and control for our control surfaces, specifically in this case for the ailerons. Slight structural improvements and additions were made for the morphing wing mechanism and its implementation, and specifically to have proper protection and guiding for the wiring. The morphing wing, as previously mentioned, was a feature required per our objectives. It is arguably one of this project's defining features. Its design and refinement were both challenging and time-consuming. Designing the mechanism always boiled down to trading between functionality and weight. Teams in our cohort were given the liberty of choosing between implementing a swept back movement or a dihedral movement to a portion of the wings. Given the rapid launch and the possible drag experienced during said launch, we surmised a swept back design would be most impactful. One initial concept included motor-actuated wings, but would ultimately cost our glider too much in added weight by requiring a faster motor or one with enough torque to be sped up in a gear reduction. In pursuit of keeping weight down, it was decided wing movements would be powered by compressed torsion springs. The mechanism uses strings to tie the wings back in a swept back position onto a helical gear from a worm gear setup, which would be located at the center of the fuselage. Since worm gears are known for not easily being back-drivable, it would allow for a motor to move the driving worm gear without a need for much torque, all as long as the helical gear was already being turned in the same direction. This is achieved by ensuring the strings are attached on opposite ends of the helical gear, with each pulling in opposite directions. This setup would allow for the wings to be released after enough rotations or several rotations on the worm gear. Due to the strong torque provided by the springs, sections of the fuselage and wings had to be reinforced with more supports or thicker walls, ultimately adding a bit more weight to the mechanism.
Hello, this is Edgar Quintero. For the last version of the fuselage, the total length increased from the initial design to a total length of 0.98 meters, as a new additional part was created, the extension part. Thus a total of 5 parts make up the fuselage: the nose, extension, wing attachment, tail bottom, and tail top. The design of the fuselage changed to maintain a consistent vertical and horizontal length of 0.038 meters and 0.06 meters respectively. Apart from the frontal portion of the nose part, and the tail portion of the fuselage, where the size gradually decreases. The change was made to reduce weight compared to the initial fuselage design. The fuselage connector is how we connect the parts together. By adding this connection design to the end of every part, having 0.5 inches extruded inwards, while the other 0.5 inches extruded outwards and drafted 1 degree, it allows us to slot the parts into one another easily. The nose portion of the fuselage was given an increase in its length compared to the initial design, and is currently 0.2377 meters, to allow more components to be fitted inside of the part. An access panel was included into the design to allow more access to the electrical components once inside to manipulate placement. The total length of the new fuselage part was 0.23 meters. The part was added to the fuselage to increase the distance between the weight of the electrical components and the center of gravity, thus artificially moving the center of gravity towards the front of the glider, as previous versions of the glider were too tail heavy, which interfered with the flight of the glider. Gated ends were implemented at the beginning of the part to prevent the electrical components from sliding backwards into the fuselage and shifting the weight backwards, causing it to be tail heavy again. For the final design of the fuselage, portion of the wings were integrated into the part and portion of it extruded, similar to the fuselage connectors, allowing the remaining portion of the wing to be slipped in, as the initial fuselage design forced us to slide the wings inside the fuselage and guess where the center of the fuselage was, creating an unbalanced fuselage due to wing placements. Additional support was added at the end of the part to strengthen that portion of the part, as test runs using the morphing mechanism caused that portion to tear apart once the mechanism was released. The launch interface was also integrated to avoid attaching manually and centering it. A cut was made into the part to allow a servo to be fitted in place in order to control the elevators. In an attempt to shift weight forward, as previous versions of the glider had 2 servos on the horizontal stabilizers to control the elevators.
As previously mentioned before, the compartment of the fuselage that is in charge of holding the components for the morphing wing mechanism had to be reinforced to avoid cracking or distortion caused by the torsional effects of the springs. This can be seen in the CAD specifically, as supports were added on one side, and although it cannot be easily recognized, this part is a lot thicker than other sections of the plane.
Both tail top and bottom make up the tail, but were split for ease of printing and assembling. The tail top has a hole cut through to allow a rod to be fitted in and rotated. A bar is then attached to the rod in the middle and is further attached to bars, which connect it to the servo in the wing support part to control the 4-bar linkage that controls the elevators.
For the power system in our glider, we selected a 2-cell, 850 mAh lithium polymer battery. This type of battery is commonly used in lightweight aircraft because it provides a strong, consistent source of power while keeping the overall weight of the aircraft low. Weight obviously is a major factor in glider performance. The lighter the power system, the easier it is for the glider to stay balanced, stable, and efficient during flight. This battery gives us enough energy to operate our servos, receiver, and electronics for the entire duration of our testing without adding any unnecessary mass. To make sure that the power coming from the battery is usable by the rest of the system, we pair it with what's called the UBEC, which stands for Universal Battery Eliminator Circuit. The UBEC acts like a smart voltage regulator. It takes the higher voltage coming from the battery and steps it down to the safe 5 or 6 volts required by our servos and the receiver. More importantly, it keeps that voltage stable even when the servos demand sudden bursts of current, like during a catapult launch, or when the control surfaces respond to quick pilot inputs. Without a UPEC, voltage drops could cause the servos to jitter or even momentarily shut down the receiver, which would be a major safety concern. Overall, choosing the right battery and voltage regulator is critical because they form the backbone of our aircraft's electrical system. Stable and reliable power ensure that our control surfaces move smoothly, our sensors stay accurate, and our flight computer has the consistent power it needs to do its job. This combination improves the glider's safety, its responsiveness in the air, and the reliability of our data collection throughout the project.
Hello, my name is Dilio Matias, and I will discuss the electrical components that were chosen and implemented in our 3D printed glider project. For the glider, we selected the Teensy 4.0 microcontroller primarily for its exceptional speed and flexibility. The 600 MHz ARM Cortex M7 processor gives us plenty of computational power to handle sensor fusion, data logging, and servo control in real time. Its compact size and lightweight design makes it ideal for integration into our 3D printed glider without affecting balance or aerodynamics. The Teensy also offers multiple communication interfaces like I2C, SPI, and UART, allowing us to easily connect the B&O 085 IMU, the SD card module, and our receiver system. Since it runs on 3.3 volt logic, it's directly compatible with most modern sensors, reducing the need for extra circuitry. Nonetheless, the Teensy proved to be an excellent choice for our glider capabilities and applications. We use the B&O 085 sensor to understand exactly how the glider moves during flight. This small device measures the glider's tilt, rotation, and acceleration in every direction. Because of that, we can capture key moments like when the glider is launched, how it moves in the air, and when it lands. One of the big advantages of this sensor is that it gives us smooth and stable measurements without needing a lot of processing from the microcontroller. It also weighs very little, so it doesn't affect the glider's balance or performance. When it comes to the wiring system, it was very simple since it only needs 2 communication lines to send its data to the Teensy microcontroller. Overall, the sensor provides us with essential flight information that we need to analyze the glider's performance and improve its design. In our glider, we included an external SD card module in our design to provide reliable onboard storage for all flight data. During each launch, the glider generates real-time sensor data such as yaw, pitch, roll, acceleration, and gyroscope values. This requires a storage device capable of keeping up with rapid logging rates, and the SPI-based SD module gives us the necessary speed and reliability. Additionally, the SD card offers large storage capacity, allowing us to record multiple full flights without worrying about running out of memory. The card is removable, which makes post-flight analysis much easier. We can simply remove the card, plug it into a computer, and immediately review the CSV data. The SD card module interfaces directly with the microcontroller using a simple SPI connection, so wiring and integration was straightforward. Since the SD card module writes in a FAT32 file system, it ensures that the recorded data is universally readable on any device. Overall, the SD card module is essential for capturing detailed performance metrics, verifying our launch behavior, and refining stability and control of the glider throughout development.
One of the main changes that we did from the previous semester to now is that for the sweeping wing mechanism, we now implemented a continuous rotating servo motor. This servo motor can continuously rotate beyond 90 degrees, and it is essential for us because this is the main component that helps us with our sweeping wing mechanism. This servo motor is connected to a worm gear, which is connected to an S-shaped hook connected to 2 fishing wire, which essentially holds back the wing mechanism in a swept wing state. This sweeping wing mechanism was not possible with a normal servo motor because a normal servo motor cannot rotate more than 90 degrees. We needed a servo motor that was able to continuously rotate until the S-shaped gear was able to go rotate a full 90 degrees and thus releasing the fishing wire so that the sweeping wing mechanism can be released. This is what we used for the sweeping wing mechanism. We used one continuous rotating servo motor and fishing wire and the worm gear and the S-shaped hook to create the sweeping wing mechanism. We also placed the microcontroller near the fuselage near the nose of the plane, so that we can gather a lot of telemetry data like gyroscopic data, altimeter data, and accelerometer data, so that we can continue to improve upon the aircraft.
When we first chose the FlySky transmitter, we were sure it would work for our purposes. As we progressed into our project, the transmitter proved to be user-friendly, making it easy to set up and control our servos to its long-reach channels. Integrating all the electrical components into the glider's fuselage, this receiver gave us enough room without compromising any required features. Since it operated at a low voltage, power distribution from the battery was enough to power the receiver and the other electrical components. In total, we used 3 of the available channels: Channel 1 for the ailerons, Channel 2 for the elevators, and Channel 3 for the morphing wing release mechanism. Binding the control surfaces to the transmitter was straightforward. The right gimbal was assigned to Channel 1, allowing the user to control the elevator by moving the stick up and down. The gimbal controlled Channel 2 horizontally, which moved the ailerons left and right. Finally, VRB, which is a variable knob, was assigned to Channel 3. Rotating this knob counterclockwise activated the internal worm gear mechanism inside the glider, which is responsible for releasing the morphing wing.
This slide shows simulated data. Since we weren't able to obtain usable real flight data yet, what you're seeing is a model of how our plane might move right after launch and during early flight. The dashed lines represent the true motion of the aircraft in the simulation, while the solid lines show what our MATLAB code estimates from simulated IMU readings. Even though this is not real flight data, it still demonstrates how the system would work. The IMU data we generate includes realistic noise and sensor bias, and the MATLAB filtering methods do a good job recovering the actual motion. You can see that the estimated roll, pitch, and yaw follow the simulated truth very closely, even right after this disturbance at around 0.4 seconds. This gives us the confidence that once we get a clean IMU logs from future test flights, the same process will allow us to track the plane's motions accurately during launch and flight. It is only just a matter of being able to get the CSV file and implement it to the MATLAB code. Once more, we're using simulated flight data results because we haven't had any obtainable real flight data from our first launch. On the top graph, you see a sharp spike in forward acceleration, representing the strong force that pushes a plane forward as it leaves the rail. The simulated spike is meant to mimic what we expect to see in real-world launch, a quick and powerful jolt. The bottom graph shows the estimated forward velocity produced by integrating that acceleration. It rises sharply right after the launch, showing how the plane gains speed fast enough to start flying. Even though this isn't real sensor data, it still helps us understand what kinds of forces and motions the plane will go through, and prepares us to analyze actual launches once we have clean IMU logs. Collecting and processing data like this is a really important part of engineering. First, it lets us see exactly what the plane is experiencing, instead of just guessing or relying on rough estimates. With acceleration, velocity, and attitude data, we can quantify how hard the launch is, how the plane responds to disturbances, and whether it stabilizes the way we want it to. Second, this kind of data helps us validate the design. Engineers can compare the measured forces and motions to what our models predicted. If the numbers match, that means our design and simulations are accurate. If they don't, we know something needs to be adjusted. Maybe the frame needs reinforcement or the launch system needs some more tuning. And finally, this data helps the team make informed improvements. We can trace vibration issues, measure structural loading, and even evaluate whether the control surfaces respond fast enough. Having these measurements ensures the aircraft is safe, reliable, and performing the way it should, which is crucial for any type of engineering project.
Control surfaces are a very integral part to any glider's design. Their implementation allows for control of certain movements in certain orientations during flight. Specifically, in our design, we had the ailerons and the elevators being controlled by 4-bar linkages that were being actuated by servo motors. This design was intentional in being able to move our servo motors away from the tail and closer towards the nose or the center of the fuselage. This would be impactful when trying to create a balanced plane to avoid having it be too tail heavy or too nose heavy, and avoid having the elevators need to have more power or more influence in the pitch during flight. These 4-bar linkages were specifically also chosen because of the simplicity in their movement, with very simple calculations from our notes and knowledge in kinematics. We're able to efficiently guess how much movement each servo motor would need to do to gain a certain amount of rotational movement at the linkage moving our control surfaces. Like in all planes and gliders, the vertical stabilizers are in charge of controlling the yaw movements. We more or less maintain this similar aspect ratio with very slight changes to the span length and to the surface area by choosing a slightly different profile than the original design. We specifically aimed for having a T-tail placement of the horizontal stabilizers compared to previous designs, which were in line with the wings of the plane. This was purposefully done to have cleaner airflow to the elevators, which would otherwise be disrupted by the turbulent flow or the disrupted flow that would come from the wings during flight. This was intentionally done so that our elevators could have more influence over the glider's pitch during flight. This also has some drawbacks, but the challenge was done with the intention of having more influence for our horizontal stabilizers on the elevators. The horizontal stabilizers provide a very integral part in our glider's flight. It specifically controls pitch, and given the circumstances of our glider's launch, there's a very high likelihood that it will find itself in a tail-heavy position at the beginning of launch and will almost immediately need to be corrected in order to avoid being tail-heavy, which would then lead to a potential stall, which would lead to an inevitable failure. And therefore, maintaining clean airflow was very integral for our design, which kind of led to the involvement of the T-tail design, which was previously mentioned in the vertical stabilizer section of the presentation. And aside from that, and implementing the control surfaces and the appropriate assembly modifications to the plane wing horizontal stabilizer parts, the general shape and design hasn't really changed from previous iterations. It maintains the same aspect ratio, span, and profile.
This image shows a screenshot taken from SolidWorks showing off a complete assembly of our first prototype of our plane.
This image shows the final design and third iteration of our glider. It includes the linkages for the control surfaces, the morphing wing mechanism, and the edits made to the wings to support the morphing wing mechanism. A lot has changed from the initial design shown earlier, and this one, a lot of material has been added, a lot of support, and a bunch of minor changes that have ultimately culminated in what we have here. Aside from the scheduled launches that were programmed between Professor Thornburn and our advisor, we had done independent tests on our own. This looped video shows one of said tests. As you can see, towards the end of this flight, our glider started pitching backwards, giving us this tail-heavy effect in which it promptly starts stalling because it doesn't have proper balance, and proper airflow, and therefore starts experiencing enough drag to where it just stalls, falls on the ground. This was a clear example of how we needed to make slight modifications to the design to try to redistribute weight in the system. And of course, this was not done with any surface controls, so there was no real way to control that pitch at that given time. But it was a clear indicator for necessary changes. All this to say, testing was very integral to seeing the immediate effects of our design choices and was probably not done enough for the sake of implementing as much changes as this project truly needed. In conclusion, we were able to adhere to many of our requirements and a majority of our objectives. We were able to successfully create a glider that was under a kilogram of weight, that was able to resist the inertial forces of a very powerful launch, to implement successful control surfaces, and a successfully deploying morphing wing mechanism. We have one last scheduled launch a little bit after the time of this recording, and we hope to use that information for our final presentations during Expo. We have many things that we would ideally change if we had more time or if we invested more time into this. There are definitely room for improvement on many aspects. There could be a lot more refinement and development of certain mechanisms and optimization in trying to reduce weight during certain sections. But for the most part, I think this project was an overall success.